Okay, so the plan for today's session is to go over Diels Alder reaction with the homolumo molecular orbitals behind the reaction. Go over electron donating groups, electron withdrawing groups, or EDGs, EWGs. The endo rule, predicting Diels Alder reaction products, like the stereochemistry behind it, the regiochemistry behind it, and then if you have time, go over the electrocyclic reaction of ring closing and ring opening. Right. So first, let's go over the HOMO and LUMO molecular orbital for conjugated systems. HOMO will mean the highest occupied molecular orbital. HOMO. LUMO, LUMO, will mean the lowest unoccupied molecular orbital. LUMO, where the number of molecular orbitals in a conjugated system will equal to the number of atomic orbitals. So number of atomic orbitals equals the number of molecular orbitals. Right. So let's look at an example. Let's look at this 1,3-butadiene here. This is a conjugated diene because all of the atoms in this system are sp2 hybridized, sp2, 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 sp2. And it could also do resonance with each other. If we have a network of adjacent sp2 orbitals, that is delocalized and conjugated, right? Where the number of electrons that are participating in this conjugation system are 1, 2, 3, 4, right? So we are going to have 4 molecular orbitals in this conjugated system here. How many molecular orbitals are we going to have in this conjugated system here, for example? Yeah, there would be 6 here because all of these 6 electrons are conjugated to each other, meaning that they could resonate with each other, right? So we know there are 4 molecular orbitals where I'm going to draw in those molecular orbitals here. Let's make a graph. Let's make this vertical line represent energy, right? We know that this 1,3-butadiene has 4 p orbitals here because we know that all of these atoms here are sp2 hybridized, meaning that they have 1 p orbital, which looks like a dumbbell shape like that, right? So let's draw 4 of them because we have 4 molecular orbitals. 2, and that's 4 right there, right? The lowest energy molecular orbital would be if all of these p orbitals are aligned to each other, meaning that they are in phase with each other like this. So all the electrons are able to overlap. No nodes, right? So all of these electrons here are able to hop around each p orbital with no problem. As we go up in energy, we are going to increase by 1 node. So this molecular orbital here is going to have a vertical node in between these 2 sets of p orbitals here, where one set is going to be in phase with each other, but out of phase of the other set, meaning that this other set here is going to go down like that. Right? Where now we see that these electrons are not able to flow throughout the whole molecule here. it's only able to flow in between these two p orbitals here, right? Which is why this is more stable meaning lower energy. As we go up in energy, we're going to introduce another node right there, 2 nodes, where now we could say these are the orbitals, no in phase there, but these two in the middle here would be in phase with each other, but the ones in the ends are out of phase. Where in this case, we only have one pair of p orbitals that electrons are allowed to flow in. In this case, we have 2 pairs. In this case, we have all 4 orbitals able to do resonance with each other. In the last one here, the one with the highest energy, we are going to have 3 nodes separating all of these p orbitals. All of these p orbitals here will be out of phase with each other. No electron flow. Right? That makes that the least stable, making it have the highest energy. So a way to think about this is, let's say that we have that 1,3-butadiene like that. We know that in the lowest energy molecular orbital, all of the electrons are flowing. So this is the hybrid resonance form of that structure right there, where we see that all of the electrons are flowing throughout the whole molecule like that, right? For the one above that, we are going to have this structure here, where we see that the electrons are only able to be in between these 2 carbons and these 2 carbons there. There are no electrons between these 2 carbons because there is a node separating them right there. Right. For this one, the next one here, we see that we could draw a resonance structure of this by moving that double bond there, pushing this double bond into a lone pair on that carbon right there. That is going to give us that double bond with a negative charge here and a positive charge here. Where we see in this resonance structure here, the electrons are only flowing in the middle of the molecule, right? The electrons are not being shared between these carbons here. Right? We could do resonance again by drawing, let's say, that arrow there, which will create this resonance structure here, where we see all of the charges are now separated. They're not flowing all throughout the molecule. This is the least stable resonance structure because it has a lot of charge and it's separated, which means that it has the highest energy because it's the least stable. This right here is the most stable resonance structure because we see that the electrons are able to flow around the whole molecule. And if electrons or charges are able to flow or breathe or be delocalized more, it is more stable, meaning it has least energy, less energy. Right? Where I'm going to draw out the molecular orbitals like this. We know we have 4. Each of these lines here represent the 4 orbitals. We said that 1,3-butadiene has 4 electrons participating in the conjugated system. So we're going to draw in those 4 electrons one by one like this. 2, 3, 4. Right? Where 2 electrons go to that molecular orbital, the other 2 electrons go to that molecular orbital. Right? We noticed that these 2 orbitals here are occupied, but the top 2 orbitals that are unoccupied. Right? So we can make a line between here and say that this section, the bottom section, is the occupied molecular orbital section. The top section is the unoccupied molecular orbital section because there are no electrons in these orbitals, right? So which one of these do you guys think is going to be the HOMO and which one of these are going to be the LUMO? Yeah, second one here is LUMO. Yeah, third one is HOMO. Right. Because this one here is, it's confusing because some people think like lowest means like it has to be lower than highest, but this is lowest unoccupied molecular orbital. Unoccupied is this section right here, where the lowest unoccupied orbital is this part right there. HOMO is the highest occupied molecular orbital, where the occupied section is down here, where this is the highest occupied section. So in this case right here, the way I drew it, the lowest orbital is higher, like in space here than the HOMO. Right? Does that make sense? Yeah. Okay. So these are the molecular orbitals of this 1,3-butadiene here. Now let's do the molecular orbitals of this alkene right here. How many? Well, we know we have 2 electrons here in that double bond, right? Where that means that we have 2 molecular orbitals. Well, let's draw those 2 molecular orbitals like this. One is there. The other molecular orbital is this. Energy is highest up here. The lowest energy one is going to be when the 2 orbitals are in phase with each other. The highest energy one is when they are out of phase, because we introduce a node right there. Where we see that the lowest energy orbital of this alkene, or in Diels Alder terms, dienophile, is this dienophile where the electrons are like everywhere in that structure, right? But we could draw resonance like this, giving us this resonance structure, a lone pair there, and a positive charge here, where now we introduce charges, and the charges are separated. So all the electrons are in one carbon only, one orbital, making them out of phase. Right. So we can make a line through here again, where we see that this dienophile here represents 2 electrons. So there are only going to be 2 electrons in that molecular orbital. Right. This is the only occupied orbital. So this is the occupied section. This is the unoccupied section. Where this is the LUMO, because that's the only unoccupied orbital. This is the HOMO, and the only occupied molecular orbital. Right. Okay. Yeah. Right. Like the highest energy one would be the one where all of the p orbitals are out of phase with each other. But it gets more complicated. Like the one in between here. Right. But for Diels Alder, we just need to worry about the diene one and the dienophile one. Right. But that's good to know for vocab questions, like conceptual questions, because he might ask a conceptual question about this. Yeah. Any other questions on this HOMO LUMO? Okay, so let's relate this back to Diels Alder. Right. So in Diels Alder, the HOMO highest occupied molecular orbital of the S-cis diene overlaps with the LUMO of the dienophile. So an S, let's go over what the S-cis diene is and versus a S-trans diene. Right. So an S-cis diene looks like this right here, S-cis. An S-trans diene looks like this right here. Right. Where in Diels Alder, we want to be in the S-cis form. We want the diene to be the S-cis form to react. Right? Because in the S-cis form, it is able to overlap or interact with the dienophile more. Because if it were to be in the, let's say, S-trans form, like that, right? Like this is able to interact and overlap, but in the S-trans form, like that thing is not overlapping. That is going away, like going out of space. Like think of it as equatorial, right? It's not going to react. But let's say you were given a S trans alkene. If you put it under heat, you could rotate this single bond right here. And when you rotate that single bond under heat, you could rotate that S trans diene into an S cis diene, and then the reaction could work. Right. So I'm going to give you two different molecules and have you guys choose which molecule would work as a diene in the Diels-Alder reaction. So those two molecules are dienes, but one of them will only work with Diels-Alder. Yeah, the left one, right. Yeah, so the S trans naturally would be the major one because it has less steric hindrance. But if you put it under heat, which adds enough energy to overcome that more stable configuration, it will go to the less stable configuration S cis. More reactive for Diels-Alder, yes, because we want it to be in this form, which is more crowded and less stable, to overlap with the dienophile more, right? Which is why we need heat to overcome that this stable S trans diene. Right. The one on the right here, we cannot rotate that bond and make it into S cis because this is in a ring. In this previous case here, this was not in a ring, so we were able to rotate that single bond. Okay. So let's draw the overlap of an S cis diene and a dienophile. We know that there are p orbitals on all of these sp2 hybridized carbons here, like that, right? P orbital, p orbital, p orbital, where we said that the HOMO of the diene will react with the LUMO of the dienophile. So let's look at what the HOMO of the diene looks like. This is the HOMO of the diene, where we see one node in the middle, right? So let's put that node in the middle right here, because we're looking at the HOMO orbital of the diene, which means that these two orbitals here are in phase with each other, but the other two orbitals here are out of phase with those two orbitals, like that. And we said we are going to react that with the LUMO of the dienophile. The LUMO of the dienophile looks like this, where there is one node in between them. So let's put that one node in between them right there, right? We want there to be an overlap between the HOMO and LUMO. So I'm going to put this shaded to show that the electrons are going to be there. That means the other side has to be at the bottom side right here. Right? Think of the dienophile at the bottom. There's going to be an interaction between these orbitals right here, right? Where we see that those electrons down there are going to be in phase with those electrons. And this empty orbital here is going to be in phase with the empty orbital right there. So the HOMO of the diene is able to interact or overlap with the LUMO of the dienophile. Right. So this is more of a conceptual question. I think it's more likely going to be in the vocab because all the mechanism reaction stuff, we don't have to draw all these stuff for the reactions. This is just like what's happening behind the scenes of the reaction, right? Where the HOMO of the diene overlaps with the LUMO of the dienophile, which makes the Diels-Alder reaction favorable. Yeah. Second double bond. Oh, it should be right here, but I shaded it in because of the orbital there. But it should be right there. Yeah. So these here, bonding, interaction, so both reactive sites have constructive meaning like in phase. You guys took physics, like that's just like, I think it's like constructive something like with the waves, with physics 7C, I think. Yeah, constructive interference, right? Constructive interference, which makes the reaction more favorable. Have constructive orbital overlap, constructive interference, orbital overlap between the lobes of the p orbital. Where this is the LUMO of the dienophile, LUMO orbital. And this is the HOMO orbital of the diene. Diene meaning two alkenes, dienophile meaning a lover of dienes, lover of two alkenes. Right? So that's the way to think about it. Where dienophile is always one alkene, diene is always two alkenes, and they interact with each other. And in Diels order, the diene is the nucleophile, the dienophile is the electrophile. Okay, so now let's go over the actual reaction of Diels order. Let's draw in the simplest Diels order reaction where we have that simple diene and this simple dienophile here. Right? This is our diene, two alkenes. This is our dienophile, electrophile. So I'm going to number it this way to keep track of all the atoms. 1, 2, 3, 4, 5, 6. This atom 1 is going to attack atom 6. Atom 5 attacks atom 4. And the double bond between 3 and 4 makes a double bond between 2 and 3. Okay? This happens under heat, where we are going to always form this cyclohexene product. 1, 2, 3, 4, 5, 6. Right? Where there used to be a double bond between 1 and 2, but we use that double bond to make a bond between 1 and 6. Used to be a double bond between 5 and 6, but we made a double bond between 4, a single bond between 4 and 5. Double bond between 3 and 4 made a double bond between 2 and 3 right there. You could have done it the other way as well. Like you could have went the other way around, which gives you the same exact product. So here's the electronic reasoning behind that. When we draw in, let's say, a resonance structure of the diene, we are going to get this resonance structure here. When we draw the resonance structure of a dienophile, we are going to get this resonance structure here. Right? Where we see the negative charge is aligned with the positive charge. They are attracted to each other because they're opposite charges. Negative charge aligned with the positive charge. So this concept here will be important because when we add EDGs and EWGs on it, these can change, right? Where that negative charge is going to attack that positive charge. This negative charge attacks that positive charge and gives you that exact same product right there. But it is clearer, it's more easy to see like where that double bond comes from the resonance structure and where the new bonds come from these arrows. And for Diels order, we said that the diene is going to be our nucleophile. Our dienophile is going to be our electrophile. So if we wanted to speed up this Diels order reaction, what kind of group do we want to add onto the diene? Electron donating group or electron withdrawing group? Do we want to give the diene more or less electrons if we want to speed up the Diels order reaction? Yeah, we want to give it more electrons, so we have to put the EDGs on them. Right? So Diels Alder reaction rate increases when we have EDG, electron donating group, on diene, or and EWG on dienophile. This is because we want the dienophile to become more positive, to become a better electrophile, and to make it more positive, we have to steal its electrons by adding EWGs on it, electron withdrawing groups on it. Right. Okay, so now let's figure out how to tell if a group is an EDG or an EWG. If you see an atom with a lone pair of electrons, that is an EDG because it has electrons to donate. If it is an R group, like a hydrocarbon chain, like a methyl, ethyl, propyl, isopropyl, tert-butyl, sec-butyl, that is also an EDG, but it does not have any lone pairs of electrons. It donates electrons inductively. Yeah, it's a weak EDG since it does not have any lone pairs of electrons, but it still donates electrons inductively into the system. Right. Also, if the atom is partially negatively charged or fully negatively charged, that is also another sign of an EDG. So an EWG would be if the atom is a double bonded carbon. So an example of that would be like aldehyde, ketone, carboxylic acid, like any double bonded carbon. Right. Another one could be halogen X, where X could be chlorine, bromine, iodine, because they are electron withdrawing groups. Right. All of these halogens here have 3 lone pairs of electrons on them, but they do not donate electrons because they are really electronegative, meaning that they want to keep its electrons. And since they are also really electronegative, they are going to withdraw electrons inductively. Whereas the R here has no lone pairs of electrons, but they still donate electrons inductively because of the hyperconjugation, not hyperconjugation, that's induction, due to the inductive effect. Right. Another sign is if the atom is partially positive or fully positively charged. Right. Because if the atom is positively charged, it wants to gain electrons, which is why they are EWGs, they withdraw electrons. And all of these, right, you have to look at the atom directly attached to the system. Look at the atom directly attached to the system, not the atom nearby, because it could get tricky. You have to look at the very first atom attached to the diene or the dienophile. Directly attached to the system. So let's look at an example. Say we have this diene right here, and we put a group like OCH3 right here. And we have a dienophile with an aldehyde on it. Right. So this is our diene right here, and attached to that diene is this oxygen right here with 2 lone pairs of electrons and a partially negative charge, which is able to donate electrons into the diene like that. This makes this OCH3 an EDG, electron donating group. Right. For the dienophile, a lot of people might think this is an EDG because of this oxygen here with the lone pairs of electrons, but that's not the very first atom attached to the dienophile. The very first atom attached to the dienophile is this carbon right here, which that carbon there we see is partially positive and double bonded. Since this carbon here is partially positive, it wants to gain electrons, making it an EWG. It wants to withdraw electrons. Right? So don't look at the oxygen here because that's not directly attached to the system. This carbon here is directly attached to the system, which is partial positive or double bonded, making that the EWG. And this could affect the Diels Alder regiochemistry because let's draw in the resonance structure here. where the EDG is able to donate electrons and give us this resonance structure here. Okay. So this EDG right here donates one set of electrons to make a double bond there. This double bond here makes a double bond between these two carbons, pushing that double bond as a lone pair onto that carbon right there, giving that carbon a negative charge. So we see our negative charge atom is on this carbon right here. Right. Now, since this is an EWG, what arrow do you guys think is going to happen here to draw the resonance structure of this dienophile? This group here wants to withdraw electrons. So it's going to withdraw electrons by directly taking the dienophile's electrons like this. Right? So it's withdrawing electrons directly like that, pushing the double bond to the oxygen right there. That gives us this resonance structure here. Right? Where in Diels Alder, we always have this pocket here that forms. This pocket between the diene and dienophile. Where in that pocket, we want the charges to be opposite to each other for it to react. Right? So these do align, so the reaction can go through as it is. Now let's look at another example where they do not align, and he could give you that on the exam, where if they do not align, you have to flip one of the groups. You have to flip either the diene or dienophile to make it align. So let's say we have this diene here with this EDG, and this dienophile here with this EWG. We know this nitrogen is partial negative with a lone pair. So when we draw its resonance structure, we get this. This is an EWG because the atom directly attached to the dienophile is this partial positive carbon, which wants to withdraw electrons from that dienophile, giving us this resonance structure here. Right. Now let's draw the pocket between the diene and dienophile. We see that the negative charge on the diene is up here, but the positive charge of the dienophile is down here. Right? Where since they do not align, they are not going to react as it is. So if they do not align, we are going to flip one of them. I like flipping the dienophile because it's smaller molecule and it's easier to draw. So flip the dienophile upside down to align the charges. So the dienophile they gave us was this with this aldehyde group. To flip it upside down, I'm going to draw it like this right here. That's the same exact structure, just flipped upside down, right? Where we said that there was a partial positive charge here of the dienophile because of this resonance structure. So when I flip it upside down, there's gonna be a partial positive charge up here now, right? Now let's draw in that same exact diene that we had earlier, where there's a partial negative charge up here, right? Because if we look at the resonance structure of that diene, we see a negative charge up on the diene, which gives that carbon here a partial negative charge. Now we see that when we draw the pocket between the diene and the dienophile, the charges do align, right? So now the reaction can go through, where the EWG has to be on the same side or ortho to the EDG in this case. Okay, so that was all about the regiochemistry of Diels Alder, like where the groups are going to be when we react. Like, do we want the EWG down there? Actually, there's more, but we'll go over that when we go over the practice problems. It's gonna be like pretty quick though. So let's go over the endo rule now, which is the stereochemistry of this Diels Alder reaction. Let's say we have this diene right here, and this dienophile right here. We know that there's going to be a pocket between them when they react, forming those neo bonds right there. And there's going to be a double bond right there as the product, right? Where the groups coming out of the diene here are called out groups. Right? So that's an out group. This is also an out group right there. The in groups are going to be the groups inside the pocket between the diene and dienophile. Right? On the dienophile, the endo product is going to face towards the diene. So the groups here are going to be endo. The groups out are going to be exo. When we put that under heat and make the reaction go through, we always get this cyclohexene product, right? Where the out group is always cis to the out group and on the same side as endo as well. So let's just say that the out groups are dashes. That makes this other out group a dash as well, because they have to be cis to each other. That makes the in groups poised to become a wedge. In group, right? The endo product is cis to the out groups. Endo. That makes the exo wedge. Exo. Right. So the out is cis to out, trans to in, and vice versa. In is cis to in, trans to out. Okay, so one more note, and then let's do a lot of practice problems on this to make it more clear and concrete. Right, because right now it's so abstract, like every out endo group. To draw the endo product, right? Think of this mnemonic here or acronym OCT-I. Right? It's like a octopus. Octopus. Where the outside groups are going to be cis to the EWG electron withdrawing group of the dienophile. The outside groups on diene is cis on the same side to the EWG on dienophile. The last note here is that the inside group on the diene are trans to the EWG on the dienophile. So let's look at an example here. Okay, example. Let's say we have this diene with that group on it, and let's say we have this dienophile with this group on it here. The first thing I do, always in Diels Alder, is figure out if my charges align. This is an R group, a methyl group, which we said is an EDG, right? Which that EDG is going to donate electrons and give this carbon here a negative charge. This is an EWG because we see the first atom attached to the dienophile is partial positive, which when we draw the resonance structure, we're going to have a partial positive charge at that carbon, because we know that when we do its resonance structure like this carbon here loses a bond, having a full positive charge in its resonance structure, right? The pocket charges align, so we could keep it as it is. We don't have to flip anything. We don't have to flip a diene or dienophile, right? So let's draw the resonance arrows of this, which are 3 arrows. That attacks that attacks that. The double bond shifts to there. And we are going to create this cyclohexene here. It might help to number the atoms like how we did earlier, 1, 2, 3, 4, 5, to keep track of every group. 1, 2, 3, 4, 5, 6, right? Where is this an out group or an in group here? Out group, right? Because it is outside of the pocket, and this is an EWG of the dienophile. And we said the endo rule, the out group has to be cis to the EWG, meaning that they have to be on the same side of the EWG. So this is going to be our product right here. Let's just choose dash. It could be wedge as well, but we usually draw the endo product in dashes, right? But both of them have to be on the same side. So this has to also be dash as well. This is the endo product. The exo product would be something like this, where there are trans to each other. Right? Back in 118A, we would always say that this product here is more stable than this product because it has less steric hindrance, right? One is facing up, one is facing down, avoiding steric hindrance, making it more stable. But in 118B, in Diels Alder, this is actually the more stable product here. And that is because the secondary p overlap, like think of it like resonance. So it might help if I draw it like this. Let's draw in the diene like that with its methyl group there. Let's draw the dienophile here, right? We could flip this dienophile and make the electron withdrawing group face towards the diene like that. So this is our diene right here, going like hovering above the dienophile with that electron withdrawing group right there. We see that there are p orbitals all around this conjugated system, p orbital here and p orbital here as well, right? Also, notice how the electron withdrawing group, which is this right here, this is an sp2 atom, this is an sp2 atom. If these are sp2 atoms, they also have p orbitals like that, right? So we want the p orbitals to be close to each other as possible to increase its p orbital overlap or resonance, right? If this was like facing away, giving us this product here, that would be like too far away. They wouldn't overlap. So the reason why the endo product is more favorable is because the secondary p orbital overlap interactions well, specifically between the carbon 2 and carbon 3 of the diene and electron withdrawing group of the dienophile is more favorable than avoiding steric hindrance. So this overpowers the steric hindrance factor. More resonance, more stable. Resonance or p-orbital overlap overpowers steric hindrance factor. Right. Where we said that this was carbon 1, 2, 3, 4, 5, 6. There's going to be secondary p-orbital overlap between carbons 2 and 3 of the diene with the electron withdrawing group of the dienophile there, because the electron withdrawing group is close enough to overlap with those orbitals there. If the electron withdrawing group was like, let's say here instead, facing away or trans to that group right there, the p orbitals here would be too far away for resonance, too far away for overlap. Right? Which is why we prefer the endo product. We prefer these groups to be on the same side to increase its p orbital overlap and conjugation or resonance, which beats that trans exo product. Right? Yeah. Yeah. These would have plus enantiomers. Plus, because both of them, this one could have been both wedges as well. Plus enant. Plus enant. If there was a pre-existing center somewhere, like a pre-existing chiral center, then there would be diastereomers. Yeah. Yeah. Okay, let's do more 2 more examples where this is going to talk about the stereochemistry of dienophiles. Because let's say the dienophile had 2 groups on it, like one at the top and one at the bottom. There's also another example where the diene could have a group on the 2nd or 3rd carbon here or here, which also affects the stereochemistry. Okay, let's move on to the next example. So let's say we have this diene with this EDG on it, and this dienophile with this EWG, and also that methyl group right there. We know the charges are going to be aligned because when we draw its resonance structure, we know that this EDG is pushing electrons down onto this carbon, making that carbon partial negative. This EWG is stealing its electrons, making this carbon partial positive, where when we imagine the pocket between the diene and dienophile, the negative charge is aligned with the positive charge. So that's good. We don't have to flip the dienophile upside down in this case, right? So we could draw in the regular mechanistic arrows, giving us the regular Diels Alder product here. Right? Where we see this is an out group because it is facing outside of the pocket. The out group here is going to be cis to the EWG on the same side of the EWG, where it could be dash or wedge, but I commonly see the product written as dashes, but you can also write wedges if you want to as well. Dash, and this has to be dash as well because they are cis to each other. Right? Now, we still have one more group here, which is this methyl group here. What do you guys predict the stereochemistry of this methyl group is going to be on the product? Wedge, right? Because this group is trans to that group right there. We have to keep it trans here. That stereochemistry has to be conserved. Since it is trans, we have to make this a wedge here. That's right. Plus enantiomer, because they could be flipped. Nice. So that was the other thing I was talking about. Mm. Mhm. Yeah, so what I mean by conserving stereochemistry is the trans configuration of this group and that group right there, like the opposite side, which these groups are still trans to each other here, right? But when we do this reaction behind the scenes, the aldehyde is actually going to be towards the diene, and the methyl group is actually going to be facing out there because we want the EWG as close as possible to the diene right there. So think of this as just like flipped like to the right like that, right? So what I mean by conserved is that this EWG or aldehyde here is trans to this R group there. Trans meaning that opposite side from the double bond, right? Which they are still opposite from each other right there. Yeah. Yeah, we want the OCH3 and the aldehyde to be on the same side because this is an out group and we want out groups to be on the same side as the EWG to increase the p orbital overlap and the row, right? But you can make this a wedge if the OCH3 was a wedge. And then this could be a dash, which is the enantiomer version of this. If this was a wedge instead and that was a dash, that would be the exo product. And that could be a conceptual vocab question. Like he draws on the thing and then he says like, why is this not the major product? And then you would say, this is an exo product. It does not increase secondary pre-orbital overlap. So that could be a conceptual question right there. Yeah. Let's do examples. Let's say we have the same diene with the same EDG and this dienophile with the same EWG, but this time the methyl group is going to be cis, right? We know the charges align, we know the arrows, we know the product. Based on the last example, the out group has to be cis to the EWG, but this time, the methyl on the dienophile is cis to the EWG, and we have to conserve that stereochemistry, conserve the cis configuration, which means that this, since it's a dash, that methyl would also have to be a dash to conserve the cis configuration. Plus enantiomer. Yeah. Oh, two electron donages, like if there's another one here, or another one dienophile. Right. Yeah, the stronger one goes towards OCH3, and the stronger one is the one that's actually going to withdraw the electrons from the dienophile, creating the positive charge on the other end. And that's going to talk about like the relative strengths between EWGs and EWGs, and that's really important for the benzene chapter. But I don't think Pascal talked about that yet, right? Like in lecture. Yeah. Tomorrow, Marby. Let's look at another example where the diene has an EDG on that carbon instead. We've been seeing examples where the EDG is on the top or bottom carbon, but let's say we had an EDG on the middle carbon. And let's say we have this EWG here. NO2 is an EWG because it looks like this right here, where the first atom directly attached to this dienophile system is that nitrogen with a full positive charge. Even though that's a negative charge in the NO2, the first atom attached to the system is fully positive charge, making it an EWG, making it want to withdraw electrons. Right. If this is the EWG, where would be the partial positive charge on the dienophile here? Which carbon? Yep, the bottom, because when we do its resonance structure by pushing the double bond here and then pushing that double bond up there, we have a full positive charge on the bottom carbon here. Okay. making this carbon here have a partial positive charge. And we have this EDG on this carbon right here with lone pairs of electrons, where when we do resonance, we're going to push that lone pair to make a double bond there. This double bond is going to make a lone pair on that carbon right there, giving us this resonance structure here. Where if that's the case, there's going to be a partial negative charge on this carbon right here. Because when we did its resonance structure, we see a full negative charge on that carbon. This is the original structure that I had in the problem. We know there's a partial negative charge here on that carbon because of this resonance structure here. Right. So let me draw in the diene file nearby. We know there's a partial charge down here. Can we continue with the reaction with the arrows? Or no, we cannot, right? Because that's good. The pocket here does not align. The charges do not align. We have to flip one of them. You could either flip the diene upside down, or you could flip the dienophile upside down to make it align. I'm going to choose to flip the dienophile, which makes our partial positive charge up here now. Right. Let's keep the diene the same, like that. Okay. Now we have everything in place. Everything is aligned. We could go through with the arrows, giving us this Diels order product. Where, let's say this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We see at carbon 5, there's the NO2 group there. And since there's no out or in group on these carbons, we could just put as dash or wedge. This OCH3 group here is on this carbon right here, which is sp2 hybridized, right? On the product, that carbon is still sp2 hybridized. And sp2 carbons are always flat. There's no wedge or dashes. So that group, the OCH3 group, will stay as a flat bond, flat because it is sp2 hybridized. Okay. This is not a wedge or dash. It stays as a flat planar bond because of the sp2 hybridization here. So carbons 2 and 3 will always be flat on the diene. Like those groups will always be flat. The things that will have wedges or dashes are carbons 1 and 4 because those are sp3 hybridized in the product. This could have been a wedge or a dash, so plus enantiomer. Yeah. Yeah, a bunch of different products. Yeah, we'll go over that after this. Yeah. Uh-huh. Yeah. Great. Great. So it will never, we know that it will never be a wedge or dash. It will always be flat. Like this flat bond here is never a wedge or dash. It's always going to be flat because of the sp2 here, right? Yeah, the octi rule would not apply because it only applies to groups on 1 and 4, right? Like let's say this was 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. The octi rule will only apply to groups on carbons 1 and 4 of the diene. The groups on carbons 2 and 3 will stay sp2 hybridized and flat. They are always going to be flat. The groups on 2 and 3. Right. Let's do one last example. Oh yeah, like one more example before moving on to the ATC worksheet. With the diastereomers, meso, enantiomers, stuff like that. But this time with different EDGs, and we have to determine which is the stronger one. Okay. So let's say we have this diene with that group and this group. And let's say we have this dienophile with this group and this group here. So the first thing I always do is find the charges. Let's look at the diene here. We have two EDGs, this EDG and this EDG here. Which one do you guys think is stronger based on what you guys see here? Yeah, the bottom one here, because it has a lone pair of electrons that can directly donate with resonance. This EDG here has no lone pairs of electrons on it. This is a weaker EDG. We always choose the stronger EDG to donate electrons into the system, right? So this stronger EDG here with the lone pairs of electrons will push electrons in, put that double bond there, and give that carbon a negative charge. We see an EWG here, even though there are oxygens with lone pairs of electrons, those are not the atoms directly attached to the dienophile. This carbon here is directly attached to the dienophile, which is partial positive. So it's going to withdraw electrons from that dienophile and give us this resonance structure here. Okay. Where we see, I'm going to highlight the important thing, the diene and dienophile. We see that there's a pocket between the diene and dienophile like that, where we see the negative charge is on top of the diene, the positive charge is on bottom of the dienophile. They do not align. So what do we have to do to align them? Yeah, we have to flip one of them, not both of them, because if we flip both of them, then they would still be misaligned, right? So let's flip the dienophile. And since these are trans to each other, we have to keep them trans to each other. This is the EDG. This is the EDG. We know there's a negative charge up here. We know there's a partial positive charge here, where now the charges do align. And we could do the regular arrows. There, there, there. Get the final product. Always draw out this template, cyclohexene. You could number it to keep track of the groups. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Where we know this is an out group because it is outside of the pocket. This is the EWG. So these two groups will have to be cis to each other from the octi row, endo row. So let's choose them to be dash. That makes this also have to be dash. To conserve the trans configuration, that ethyl group would have to be wedge. Right. Carbon 2, we have this isopropyl group, which was sp2 hybridized and is still sp2 hybridized, which makes that flat and planar. No wedge, no dash. So this is the answer plus enantiomer. It would not be this. Right. This would be the answer if you like just drew it as it is, the arrows, without flipping anything. Right? Like let's say you saw the product, I mean the question like this, and you just went straight for the arrows like that. When you just go straight for the arrows without aligning charges, this is the thing you would get. But that is not right because the charges didn't align. Right? We have to go through the whole like charge alignment first, and then get the right regiochemistry of the Diels-Alder reaction. The stereochemistry of this reaction is with the endo row, octi row. Yeah. Mm-hmm. Yeah, so that's gonna talk about like which one's gonna be a stronger EWG, right? Like the nitrile group or the aldehyde. The nitrile group is gonna be a stronger EWG, so that's the one that's going to withdraw. An aldehyde, like, let's see. Are you talking about this dienophile? Are you talking about like two aldehydes? Or yeah. 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 Oh, let's see.
And then I was looking the way like I was talking about get two.
Oh, two major products. Right. Yeah, because the positive charge could either be here or here, and then that could mix up the products.
Yeah.
Give you a mixed product.
Because the carbons are.
Yeah.
Okay.
Yeah.
But like versus that, there's like one that's clearly withdrawing another. Like you can differentiate between them. Okay.
Yeah. Yeah. Okay, try these problems for like around 5 minutes, and then I'll go over these problems here. Yeah. Yeah. Oh yeah.
Everything else in the work. I can't visualize.
Right. So this one here, they try to trick you by putting the diene in a weird configuration.
Yeah.
This wasn't there before, right? Like this.
No,
this
you
one.
can.
So we could redraw this into this form right here. Like let's draw this the diene that you're used to, which is this right here. We could say this is 1, 2, 3, 4. 1, 2, 3, 4. We know between 1 and 2, there's a ring like that, right? And then we know that these are EDGs, which puts negative charges here.
Yeah, over there. Electron flows on that way.
Right. Oh, but in this case, it doesn't really matter because
Yeah,
they're the same. So this is the thing that's going to happen here, like that.
Okay, I see.
Right.
And then,
So you just have to rotate the molecule to make it more clear to see.
And then would this become a dash then? Because this is, or no, this bond right here would be dash.
Dash, and this would have to be dashes as well.
No, that's dash.
Right, but this is going to be planar because SP2. Right. Yeah, that's what it looked like at the end. Nice. Okay. Yeah, no problem. Yeah, no problem. Where my phone go?
Oh yeah.
Oh. Dang. Wait, which college or school? Oh, SF State, I see. Oh, yeah, sorry. You? Yes. Yep. Yeah. Yeah. Oh, okay. Yeah, if there's like different EWGs on it, they would give you diastereomers. Like that's the case where they give you diastereomers, where the groups are different. Yeah. For this part, A. Oh, A. Let's see. Um, oh, oh, this is the diene. This is the infinity.
Let's
Oh, okay. So this part here is a tricky thing, right? Because the thing that's going to be attached is that carbon and that carbon right there. Because you know how this is the diene right here? Think of that as the
It's gonna
in
be a
group.
bridge.
Yeah, it's gonna be a bridge
Oh.
in the thing where this is in group, so it's gonna be trans to EWG. So
So that would be like
yeah, like that, right, right. Where the
it's-
right, and then we would have to now include stereochemistry here. If you made this a wedge, right? You know how this is the pocket between the diene and dienophile? You know how these are
oh,
the
because
in
that's the
groups?
N groups.
Yeah, so they have to be
Okay,
trans to the EWG. So if you made this a wedge, this would have to be a
A
dash. That's right.
So these would be
Dashes.
dashes.
Yeah, that's right. A plus in the enantiomer. Right, right.
Just trying to imagine a model kit for this.
I know. Yeah, it could be more like useful to see with the model kit. Yeah. Yeah. Uh-huh.
Where did you get in this case?
Yeah, you would get enantiomer for this one and this one. So you get 4 different products.
4 different. Okay, yeah.
Yeah.
Could you give an example?
Example like that?
Drawing with.
Yeah. Yeah, with the partial positive
Mariah
charges.
didn't explain like.
Oh, like the alignment.
She just went straight.
Oh, I see. I
Yeah,
see.
she's like, you have 5, 6, 5.
Oh,
And then you could attach it. I was confused.
yeah, yeah. I'll go over an example of that. Yeah. Uh-huh. Yeah. Yeah. Hello. Right. So this is the EDG right here, which donates electrons inductively. And imagine this was an OCH3 group or NH2 group with a lone pair of electrons. That would make a double bond there, push this double bond to make a double bond there, and then that double bond would make a lone pair of electrons there, making that negative charge. It's like that phenomenon or principle.
What if it
Oh, like no, nothing there.
Yeah.
Then this group could either be on top or bottom. It's gonna be the same thing because if there's nothing here, it's the same exact product, just flipped upside down.
So it doesn't. It wouldn't matter which side.
Yeah, yeah, doesn't matter. Both sides could be negative. Yeah, but if you draw in like the product with the EWG is on top and the other product with the EWG is on bottom, that's the exact same thing. You just flip, right? Uh-huh. Yeah. Mhm. Yeah. No problem. Yeah. Yeah. Oh yeah. Sorry. Thank you. Yeah.
Um, how do I tell the partial positive negatives
Mm.
with like just a metal?
Yeah. So think of it as an electron donating group with a lone pair. So imagine if it did have a lone pair. Like where would the charge go if it did have a lone pair?
Like here.
Yeah. Oh, like
Oh,
down
because it can
here.
be because carbocations are somewhat exclusive.
Like they push it
It would like kind of go to that
and then it would go make a double bond there, right?
there.
That pushes this double bond here, and that pushes that double bond to make a lone pair, where that's the partial negative charge. Yeah, I know. Yeah. Wait, let's see. That's the case. Yeah, that's right. That's right. Okay. Yes. Right. So from a diene and a dienophile, you know how there's going to be a pocket between that carbon and that carbon and that carbon and that carbon? Let's imagine a pocket there, or you could like draw dashed lines to make it easier to see. If the group is out of the pocket, then that's an outgroup. So if it's like vertical, think of it as outgroup. If it's slanted towards the thing, that's an in-group. Right. So if it's vertical out, that's out.
Something like that would be in.
Yeah, something like that would be in. No, that wouldn't work. That wouldn't work. Yeah, that looks like an extra bond. Yeah, it really clearly drawn. Yeah. Right. Yeah. Uh-huh. Yeah, no problem. Oh shoot, sorry. Okay, let's go over the first two, and then after the first two, I'm gonna go over an example where we create diastereomers, because these here are going to create enantiomers, but after that, I'll go over an example which creates diastereomers. So we first have to locate our diene and the dienophile. This highlighted portion here, this highlighted portion here is our diene. This highlighted portion here is our dienophile. We can number this as 1, 2, 3, 4, 5, 6, right? The next thing I do is I draw the pocket between the diene and dienophile. So let's look at this group here. Is this an out group or an in group? It is an in group because it is inside of the pocket here. If it's inside of the pocket, would that have to be cis or trans to the EWG based on the octet rule, endo rule? Trans, right? Where these are EWGs because the first atom attached to the dienophile are these partial positive carbons there, right? So let's draw that template of a product there, where this is 1, 2, 3, 4, 5, 6. Let's say that the EWGs are dashes. We know that these are in groups, which makes them trans to the EWG. If these are dashes, the in group would have to be wedges, like this, right? Where it forms a bicyclic ring. The first ring is this cyclohexene. The second ring is on top of that ring, right there. I could redraw this to make it more clear, where we could draw it like this. Where this is the cyclohexene right here, and from that cyclohexene, we have a cyclopropane coming out of that, right? Where that wedge is going up, so that's why these bonds are going up. These bonds are going down, so those bonds are going to go down. Okay. It's the same exact representation, just different like way. Okay. Okay. So I know like Pascal might put something like this on the exam in this form, but what that means is just this right here, like into that like that kind of book shape. Okay. So now we know this is an EDG. Where would be the partial negative charge on this diene here? Yeah, we could imagine it as like with lone pairs of electrons, which would give the bottom carbon a partial negative charge there, right? This is the dienophile with this EWG. where the partial positive charge would be at that bottom carbon right there, based on its resonance structures. From here, draw the pocket. The charge is dual line, so we don't have to flip anything. Let's draw that template out. This group is outside of the pocket, which is an out group. And based on the Endo rule, the out group is cis to the EWG. So if that was a dash, this would also have to be dash. Plus enantiomer. Mhm. So let's say we have this diene right here with, let's say, this EDG in that R group on that carbon 3, and this dienophile here. And let's say that we have an aldehyde there and a nitrile here, right? Depending on your professor, you could have 2 or 1 product, right? Because we know these are 2 different EWGs. Those 2 EWGs could give you 2 different products with 2 different enantiomers. But if your professor says you have to choose the stronger EWG, then you'll only get 1 product with its enantiomer. So let's just show both diastereomers and its enantiomers, where we know that this is the stronger EDG than this R group there, which means that our partial negative charge is on that carbon when we do the resonance structure, right? Both of these are EWGs that can do resonance, because this CN there is a C triple bond N, which is a strong EWG. It could do resonance there, giving this carbon a positive charge like that, or it could do resonance here, giving this carbon a positive charge. So we have 2 positive sites. We have that positive site and this positive site right here, right? So one of your products could look like this. Wait, not cyclohexene. This out group here has to be cis to the EWG, so it would be like that, CN plus enantiomer, right? We could have flipped this upside down to give us this configuration instead, which changes the regiochemistry of this reaction. Because instead of the aldehyde being ortho, oh no, you guys learned ortho metapara? Okay, yeah. So that ortho metapara stuff is more for benzenes. The aldehyde here in this product is 1 away from the OCH3. Wait, the nitrile, because the based on this one right here. Nitrile is 1 away from the OCH3, and the aldehyde is 2 away from the OCH3 plus enantiomer. These 2 products are diastereomers because, oh wait, they are not diastereomers. They are constitutional isomers because they have different connectivity, not diastereomers. Wait, can you even have diastereomers in Diels Alder? Oh yeah, pre-existing process. Oh, right. But we can't have pre-existing stereo center on the diene or dienophile because all of the atoms of the diene are sp2. So we can't have any chiral centers there. We can't have any chiral centers on the dienophile because those are also sp2 hybridized. So we can't have pre-existing stereo centers on the diene or dienophile, but there could be a pre-existing stereo center if, let's say, yeah, like this right here, right? Then these would be diastereomers. Oh wait, no. Yeah, they're still constitutional, right? So no diastereomers in Diels Alder, right? This right here with this enantiomer, or its constitutional isomer with this enantiomer. No diastereomers. Because yeah, touching the top. I know it's file. Oh, right. Yeah, they are diastereomers. Right, yeah. Because this right here would not be enantiomers anymore. Yeah, that's right. Because these groups here are the ones that are changing. Like those ones there, not this bond. That bond does not change. So those are diastereomers. Right. Yeah, that's right. Uh-huh. If you had the bridge thing there, the bridge itself would not be diastereomers because the bridge itself is the in group, which will also flip as well. So you can flip that into a dash bridge there, right? But the stereochemistry on the R group of the carbon 2 or 3 would not change, making diastereomers. Right. So if we had something like that, let me draw out the diastereomers actually to make it more clear. Right. So we have that. Or we could have this right here. That because we know that the out group has to be cis to the EWG, which could all be dashes or they could all be wedges there, right? This pre-existing star center on the R group here does not change, so that's why these are diastereomers, right? Same as for this one here. So these are diastereomers, but this set here are constitutional isomers from each other. Constitutional isomer here, like here. Right. So this could get tricky if we had, let's say, something like this. Let's say we had this diene and dienophile here reacting with heat. Right. Yeah, we have to redraw it by rotating this single bond and make that into S cis diene, because right now this is an S trans diene. So let's number this 1, 2, 3, 4. 1, 2, 3, 4. Oh, CH3. Carbon 3 has this R group here. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Yeah. So this is the redrawn version after the single bond gets rotated here, which this is our diene, and these are the groups on that diene right there. Right. So Diels Alder can get tricky because your diene could not be in this form. It could be in some kind of weird rotated form. It could be in this S trans form, but you just have to like rotate it, flip it until you get to like this this form right here. Yeah. Where we see that the negative charge is going to be on that carbon of the diene. And in this case, since we have a symmetrical dienophile, we have positive charges equally here, where when we get the product, let me just change it so then we get multiple products. Let's say aldehyde there, right? One set of products could be this. This is an out group, so they have to be cis to the EWG, cis to the EWG. The R group here stays the same. Can we say plus enantiomer for this here? No, we cannot say plus enantiomer. This is a diastereomer because the only thing that changes are these here. This does not change. This group here stays as a dash, but these things can change into a wedge. So these are, you can do plus enantiomer, plus minus, you put plus diastereomer, or just draw out the whole thing with the switched bonds. But if you put plus diastereomer, that's more vague because you don't know what diastereomer is going to be like reformed. Like you might say this is wedge, but it's probably more safe to draw out these switched and that the same for the product. Okay. So this is going to form diastereomer like that. And yeah, diastereomers. Okay, we could form constitutional isomers as well, because let's say we flipped that dienophile to put the aldehyde on top and nitrile on the bottom. Exact. But now aldehyde on top, nitrile on bottom. Wait, let me make this smaller. Right. Where these two molecules here are diastereomers of each other, these two molecules are diastereomers of each other, but this set are constitutional isomers to that set right there because of the connectivity. Right, these are diastereomers because all of these can change on where the reacted carbons are of the Diels order. This carbon here did not react at all. This carbon there stays the same. So that is going to stay the same, making these diastereomers because some chiral centers change, some chiral centers stay the same. Okay. I think that's it for Diels order reactions, like all about the stereochemistry, regiochemistry. Let's do some more examples on this and then move on to electrocyclic rings, like ring opening, ring closing with the conrotatory, disrotatory. Let's try one with the alkyne here. Actually, let's do these three. Let's do these three for the next 10 minutes. Oh, right. So think of the alkyne as a dienophile, right? Where let's rotate it and make the alkyne like right there. As like you know how a dienophile is usually right here where we try the mechanism arrows. Let's rotate the whole thing where the alkyne is right there. Think of that as a dienophile where we do the exact same mechanism arrows, but we only use one of the
Oh,
bonds
okay,
where
so
the double bond is still going to be there.
so it just becomes an alkene.
An
because, like,
alkene.
so, oh, okay.
Right. And if that's an alkene, what is the hybridization of that carbon if it becomes an alkene? sp2, what does that make this bond here? Planar. So it stays as planar. There's no wedge or dash on that side.
So octyrole does not apply
Yeah.
because of SP.
Right,
Oh,
right.
okay.
Octave rule only applies on sp3 carbons that can have chiral stereochemistry.
Yeah.
Right.
Okay.
Yeah.
Mhm.
Uh-huh. I think today should just be like the Diels Alder stuff because I want to go over like the ranking dienes like in dienophiles, which ones will happen faster. And then for tomorrow's session, I'll go over the electrocyclic ring opening, ring closing, convertatory, distillatory stuff. Yeah, yeah, I'll go over that in my house tonight. Yeah. So I don't want to rush this concept. I don't want to rush the electrocyclic stuff. I know, like he was like, "Oh shoot, I'm behind. Let me pick up the pace," and then he's like, "Midterms like 2 weeks." Yeah. And in 1 B, like always at the end of it, like the last 2 weeks, like and all professors, Helix and the Siri, that's when people get like overwhelmed and stressed out. Because that's when a lot of things come in, like a lot of reactions, mechanisms. Yes, aldehydes and ketones. Yeah, yeah. That's like when I like was about to give up too. Like when I took when I CB, I was like, this is getting so hard. So like try to get ready for it, like ahead of like try to get ahead or something like that. Aromaticity, yeah, definitely. Pseudo-cast. Oh, you didn't know the pseudo-cast isolation, alkylation. Wait, that's good, that's good. Well, I think pseudo-cast will come after like the other stuff, like bromination, chlorination, sulfonation, nitration. Oh, all of it tomorrow? Oh my gosh. With the orthopara director, meta director. Oh,
Well, he's already
EWG, EDG.
okay, oh, yeah,
Right, but it's gonna take time to do the mechanisms behind those reactions as well, like the
he goes really
bromination.
fast.
Oh yeah.
He doesn't show them. Yeah, he doesn't care.
Yeah,
He showed us his
Yeah.
mechanism first.
Yeah. Oh my gosh. Wait, what was the mechanism for the first midterm again? The
Was the hydration.
Oh, hydration. I see. And he just skimmed over that in lecture, so he expects you to like know it. Dang.
What the one he? I don't know why.
The mechanism on that? Oh yeah. That was the longest one, probably. A lot of repeat steps. Okay. Where'd it go? Okay, so for this first problem here, it might be confusing on like where the dienophile is, but our dienophile is going to be this triple bond alkyne right there, because this is our diene. And for that dienophile, we just need one alkene, which our one alkene or like one pi bond. And our one pi bond is going to come from that triple bond right there, right? So the diene is in a good format because that's the format we use to when we draw the mechanism arrows. But let's rotate this structure into this form where we could see that the diene is going to be that diene right there. And the dienophile is going to be this dienophile right here, right? Where that triple bond is bonded to two ketones right there. Where these are EWGs because the atom attached to it is partial positive and double bonded. Let's draw the pocket between the diene dienophile. We know that these are in groups, making them trans to the EWG. So let's draw in that template product, the cyclohexene. We know that there's going to be a bridge because these in groups are connected to each other. But the bridge is going to be 1, 2, 3, 4 carbons long. This, then connect those two carbons like that. Right. Where this triple bond here, one of its bonds was used to do the Diels Alder reaction, making this triple bond turn into a double bond alkene right there. Where these carbons here are sp2 hybridized, making them flat and planar, making those carbons there also flat and planar. Like this. Okay, here's a conceptual question. If he gave you this on the exam and he asks you which one is the stronger dienophile or which dienophile will make the Diels Alder reaction happen faster, which dienophile would you choose? Like which dienophile would increase the reaction rate of Diels Alder? This dienophile or this dienophile? Yeah, the one on the right, because we said EWGs make dienophiles faster, right? And we'll go over more of those ranking problems, like rank the following dienes, dienophiles from like the strongest to weakest. Yeah, you can use this as a dienophile as well, where if you introduce another diene, it would select for this dienophile because this is the stronger dienophile than this one here. Right? If you have an excess amount of dienes, once it reacts with this the first time, there's no more dienophile here. It will react with this other dienophile here. Yeah. Okay, so for the next one, we do the same thing. It's oriented really weird because we're used to seeing Diels Alder into this kind of format where the diene is spaced that way and the dienophile is spaced that way. But they are slanted now, right? Where we see that the diene is this highlighted portion, the dienophile is that highlighted portion right there. Let's redraw them into its form that we are used to seeing it in, which are these forms right here. Right? I'm gonna number this 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We see at carbon 2, there's a methyl group. Carbon 4, methyl group. At carbon 6, there's an NO2 group. So the way I drew it right here, I can't just like do the mechanism arrows right away because I have to make sure that I drew them in the right orientation. So I have to look at the charges here, right? So where would be the negative charge on this diene here? Yep, 1. So this could be a negative charge here. And on the diene file, what would be the positive charge? Down, right? So the way I drew it first, the way I oriented it, this would give us the wrong product if we just went straight through. We would have to flip one of them now. Because I didn't know like where the charges are as I was drawing it. I was just drawing random things because I wanted to draw it in this form first and then align the charges afterwards. But I drew it in the wrong orientation where I'm just going to flip the dyno file upside down to align the charges. Right. So let's flip that dyno file upside down. Put the NO2 down there. Now the charges will align because the negative charge here will be aligned with that positive charge. We could go through with the regular mechanisms. Methyl group there. This out group is going to be cis to the EWG there, right? Plus enantiomer, because there is no pre-existing stereochemistry on that R group right there. If there was a pre-existing stereochemistry, then we cannot put that plus or minus or plus enantiomer sign. We would have to draw out the whole thing again with that stereochemistry maintained, conserved, but flip these two stereochemistries here for the diastereomer version of it. Right. Yeah. Let's do this one. So in this diene here, we have 2 EDGs. It depends on your professor. If he wants you to use the stronger EDG, you would only get one set of enantiomers, but you could have 4 answers here, where one set is the constitutional isomer of the other set, because we could have a negative charge either on that carbon or this carbon right here, right? Where in the EWG, we have a positive charge here. So let's draw the pocket and see where the out and in groups are. This is the in group, this is the out group, this is the EWG. Let's draw that thing there. The out group is going to be cis to the EWG. The in group, which is this methyl group here, is going to be trans to the EWG. Since I made this EWG dash, that methyl has to be wedged to be trans. Plus or minus. But we said that the negative charges are on both carbons because we have 2 EDGs here. So let's just flip this EDG like this. Right. Using this EDG, we could have this constitutional isomer here. And it's enantiomer version as well. I don't know about Pascal, but Nassiri would say that this is the only set of answers because this is a stronger EDG than that methyl group right there. Since this is a stronger EDG, there would be a more negative charge on that carbon right there, where that more negative charge will align with that positive charge, giving us this major product here. Since this is a weak EDG, there's less negative charge here, giving us less of that product right there. But I don't know if Pascal wants both products or not. I would ask him in office hours about this. Any questions on this one? Okay, so for the remaining of the session, let's do these ranking problems here. Where for this problem, they gave us a list of dienes, and we have to rank them from decreasing reactivity, where 1 is going to be your most reactive diene, 5 is going to be your least reactive diene. And for the second problem here, we're going to rank dienophiles, where 1 is going to be the most reactive dienophile, and 6 is going to be your most reactive, least reactive dienophile. Where we said for Diels Alder reaction to happen faster, we want EDGs on dienes, EWGs on dienophiles. The other thing that increases the reaction rate is if it's fixed and locked, meaning that, let's see. Let's look at the first example. Work on this for around 3 minutes. Right. All right. We can't rotate the bonds, or we can't flip them, rotate them. Yeah, that makes them stronger. Yeah, because there's no way for them to like flare around, move somewhere else, and interact with something else. They're locked into that position, making it restricted and happen faster. So for these ranking problems here, I like to find the extremes first. I like to find the top one and the least one first. Let's find the least one first, right? Where one of these dienes here can never do Diels Alder reaction. Which one of these can never react? Which one of these dienes can never react? Yeah, the second one, because it is in the S-trans configuration and we cannot rotate that bond because it's part of a ring. So that is number 5, the least reactive. Now I look for my most reactive. The most reactive is going to have the strongest EDG. Which one of these has the strongest EDG? Right, the fourth one, because it has an oxygen with 2 lone pairs of electrons that can donate electrons. And not only that, but it is also fixed because it's part of a ring. So that's our most reactive diene. Then everything else is in between, right? Where we know that this is the diene for that part, this is the diene for this part, and this is the diene for that part. We know that these two here have EDGs on them because they have R groups. This is an R group, so that increases the reaction rate. That's an R group, so that increases the reaction rate. This right here has nothing on it, right? So do you guys think the R group will increase the reaction rate or decrease the reaction rate? Increase the reaction rate, right? Which makes this one here number 4 because they have no EDGs on them, right? So now we have to see which one is going to happen faster here. You know how when we react diene with dienophile, the dienophile is like right there, dienophile is right here, right? Which one of these looks like they could reach the dienophile better? Like which one of these has less steric hindrance? Yep, the second one, because there is more space here for overlap. Making this number 3 because this one has more steric hindrance, right? Because of these R groups here, blocking the way because this is where the dienophile is going to be, but this R group is in the way of them overlapping with each other, right? So that's the ranking system for that diene. Now let's do dienophile, right? So for dienophiles, we said we want EWGs on here. One of these dienophiles has EDGs on them, and which one would that be here? Yeah, the methoxy on it. Oh, or the methyl as well. Yeah. The methyl is an EDG, but this is also an EDG as well, right? So now we have to choose which one is the stronger EDG. Yeah, the OCH3, because the OCH3 here has lone pairs of electrons on them. This has a strong EDG. This is the least reactive, number 6, right? And we also have a methyl group here, which is also an EDG. So that's going to be the second least reactive because we do not want EDGs on dienophiles at all. This is a stronger EDG, so that's why this is the slowest, right? Now let's look at these ones here. These ones are EWG, 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 EWG. This one has no group on it. So that's going to be number 4 because all of these other ones here are better than that one with no group at all, right? So now we have to choose which one has the stronger EWG. The one with the stronger EWG will be the one that can do the most amount of resonance, can withdraw the most amount of resonance. Let's look at this dienophile right here. This dienophile here has this EWG and this EWG right here that can withdraw that electrons like that. And here, right? And this is also fixed because it is part of a ring. And if it's fixed, it will be faster. So this is our most reactive dienophile because it's fixed in a ring and it has 2 strong EWGs here, right? Our second most reactive is going to be the one with 2 nitriles, and then the third one is going to be with only 1 nitrile here. Yeah. Oh, right. It is that's a good point. Like if it's more stable, it's less reactive. But we're talking about the electron withdrawing ability here, not the reactivity ability. Right. Because Oh, okay, I see why now. So when we draw its resonance structure here, you know how this oxygen will have a negative charge and this carbon will have a positive charge here? We know this nitrile here has a C triple bond N. If we draw the resonance structure here, this nitrogen will have a negative charge and this carbon will have a positive charge. Now we have to see which carbon here will have the stronger positive charge, right? Well, you know how oxygen is more electronegative than nitrogen is? Oxygen is able to keep that negative charge more, making this positive charge last longer. This nitrogen is less electronegative, so it's willing to go back and give that carbon its electrons back. So since there's a bigger positive charge on that carbon, it's a better withdrawn group because it wants to gain more electrons. Right. Yeah, you would want a more positive charge connected to the dienophile to make it faster. Yeah, yeah. Oh, like if it's more stable, oh, right. So we're not talking about stability here. We're talking about like the reaction rate, or think of it as the withdrawing ability, right? Where the power of this EWG to pull electrons from that dienophile right there, it will become stronger if this is a bigger positive charge. So we want more positive charge, more withdrawing power, right? So we don't think about like stability here, right? Or you could think about a stability where we want this to be less stable. We want this to be more positive charge. Right? Yeah. Yeah, the electronegativity difference here, and also the fixed factor here. Like it's fixed in this position here, right? Fixed position. Yeah, fixed positions would make it also more reactive. And I remember him mentioning that in lecture as well. Like fixed groups will make the reaction rate go faster. There could also be, let's say, the alkyne dienophile, the triple bond alkyne with the groups coming out of it linearly. Yeah, yeah, and that's it. Yeah.